Yeah.
Can you hear it now? Perfect.
Yeah.
And now I should hide it again, yeah. Right?
But you'll need to pull it up again.
For what?
Well,
Can you hear me?
No, it's okay.
Can you hear me?
I'm already set up. I just
So-
Wait, you guys can't hear me?
I didn't hear anything.
Hello? Hello?
Yeah, this is Alex.
I already.
Requested that I push this. Yes.
Because when it didn't work for me when it was in there, so you have to get out of the slides. Oh, it's not even moving that. Okay.
Is the volume on your laptop on?
Yeah.
Can you hear? Oh, okay.
Sorry, so what?
It should be, what if you go into more? What are those things? Oh, no,
No, should
never
I
mind,
hide?
never mind.
Are we now good with sound or
Yeah, I
not?
think
Yeah.
we should be good.
So I can hide it and.
Yeah,
Yeah.
Now it should be fine.
Yep.
Okay.
And then, do you need any of these? Don't need this. Laser pointer.
I like
Pointer for me.
physical pointer.
Yeah, most physicists do, I've found. This one.
Well, I finally, no, he has written the comments, but we finally got it easy, it's the second try to the last one. She put it together. Like that, sort of, targeting location, it was actually. You go first. Yeah, where I'm not. Okay. Where the plant is there, and the food is nice and spicy. So it's a good one. Wait one moment, just to accommodate load strugglers. So. With people, I don't see the Zoom. But they will speak up. Yeah. So if something is not right, then send a text to you.
Okay.
It's like this, I kind of will ask questions.
Okay.
Okay, maybe we can start. It's a pleasure to introduce Jaroslav Trnka, who goes by Yara. And Jaroslav is from Czech Republic, initially getting his undergraduate degree at Prague and doing his obtaining his PhD from Princeton, working in with Nima Kanihamed and collaborators. He is most known for his contribution to the Amplitude program and with the idea of reformulating field theories in a completely different way. After Princeton, he was the postdoc at Caltech and becoming a professor after that at the University of California in Davis, where he quickly rose to the rank of associate and then full professors. he is visiting here today and tomorrow. And with that, I leave the floor for you.
Okay, thank you very much, Maxime. Thank you very much for the invitation. So I will talk about some progress in the field of scattering amplitudes. I will give some more general introduction, and then I will kind of focus more on parts of my own work on the relations between amplitudes and geometry. Most of the slides are very accessible. I put a small magnifying glass in the corner of the slides, which are slightly more technical, so you can skip them, you know, if you pay attention, just to give a little bit more details of some of the things I will be talking about. So let me start just general. The scattering of elementary particles is very important in experimental particle physics to study new physics at colliders, to reveal fundamental laws of nature through the interactions. We measure the outcomes of scattering experiments, and by detailed understanding of what is going on, we can distinguish the standard model physics from some new physics. But I will look at the same problem from the theoretical point of view. And we will work in the context of quantum field theory, which gives us a theoretical framework how to describe the scattering process. And because of quantum mechanical nature, for the initial states, we can have various final states. And the probabilities that given final state is realized is given by the mathematical function called scattering amplitude, which depends on initial and final states, on some kinematical data, momenta, spins, helicities, spin structures, other things that are relevant. And this is what we will calculate, and this will be our focus the whole talk. But of course, in order to actually turn it into a quantity which can be measured, we need to do some further work and calculate the cross-section, integrate further over the phase space. So our focus will be on this part of the story, on the scattering amplitude. Now, the standard definition, definition of the quantum field theory gives us a recipe how to calculate these scattering amplitudes, at least at weak coupling. If we have a small parameter in the game, we can use perturbation theory. So we take the amplitude as a function of this parameter, and we expand in this parameter. And Feynman, Schwinger, Dyson, and others gave us a prescription how to do these calculations. We expand. We can use the diagrammatic interpretation of each term in the perturbation theory in terms of Feynman diagrams. We start with Lagrangian. We derive rules, and we draw all Feynman diagrams, and we evaluate them. And the perturbation theory naturally organizes itself as the loop expansion in these Feynman diagrams. So the leading contribution is tree-level amplitudes, then subleading amplitudes with one internal loop, with one unfixed loop momentum that we have to integrate over, and then 2 loops, 3 loops, and so on. Of course, in most of the theories, the vast majority of the theories, this is an asymptotic series. It's not convergent. It's even in principle, if we are able to calculate the corrections to all loop orders, we are still missing some non-perturbative data. So the radius of convergence is 0. In one very special theory I will talk about later, it's actually a convergent series, but this is very special. So in general, it's just an asymptotic series. Now, focusing now on the perturbation theory. So in principle, the problem of calculating these amplitudes is solved. I just kind of reviewed the Feynman diagram prescription. At weak coupling, we know in principle how to calculate these amplitudes. But there are practical computational difficulties. And even at tree level, at this leading order, when we don't have to do any further loop integrals, which is a difficulty by itself, there is a huge complexity in the number of these Feynman diagrams and how to calculate tree-level amplitudes, let's say, for higher multiplicity. And this is exactly the point where the first hints of some new structure, which is invisible in the standard approach, emerge back in 1980s. And in this case, the object of interest were amplitudes in quantum chromodynamics in QCD. And these amplitudes are needed for the accurate prediction of the standard model background. If we want to see some new physics, we have to accurately calculate what is already there in the standard physics. And the most complex part in these QCD background calculations are gluon amplitudes. This is not, of course, the full story, because we calculate amplitudes of gluons. We have to then also involve some Parton distribution functions, actually, to put it into some physical quantities. But if we kind of zoom in into these amplitudes, these gluon amplitudes are really quite complex. And this is just the way how the problem is set up. There is a huge number of these diagrams. The Feynman rules for the vertices in these diagrams are quite complicated. If we glue them together, we get big expressions. And but they were needed even back then. After the discovery of QCD in early 1970s, people started to calculate these gluon amplitudes. And by the late 1970s, the most complicated process was 2 to 3 gluon scattering. So 5-point amplitude at 3 level, how we would call it. And the 4-point amplitude is relatively simple. Like after a few hours of work, anybody can do it. But the 5-point amplitude already is 24 pages of algebra like that, if you really do the straight calculation from the textbook. When each of these very small dots here are some Lorentz contractions of momenta, polarization vectors, yeah, some kinematical data which enter the game. Now, in early 1980s, in 1983, the new superconducting supercollider was approved, which was supposed to be built in Texas in late 80s, early 90s. And there was a theoretical demand for higher point calculations of this kind, higher point gluon amplitudes. Now, the energy of that collider were supposed to go all the way up to 40 TeV, which meant a lot of gluon scattering. And the next process on the theoretical wish list was a 6 gluon amplitude, 2 gluon going to 4 gluon. And this is what people started to calculate. And this calculation was completed in 1984. And the practicalities it required to evaluate 220 Feynman diagrams, and it was roughly the raw result was 100 pages of algebra, similar to what I showed before. And the paper written by Stephen Park and Thomas Taylor went into the publication with a very small title, Gluonic 2 goes to 4, and very short abstract. The cross-section for 2 gluon to 4 gluon scattering is given in a form suitable for fast numerical calculations. So that was this was their objective, to give experimentalists a formula they can use for fast numerical calculation. And the result was compressed to 14 pages out of this 100 pages of algebra. There is a list of some coefficients. There are some basis terms, a lot of symmetries. They use some artificially n = 2 supersymmetry just to organize the results in a better way. Anyway, so this was the result. The paper is just that. There's nothing more. The only thing in addition is just a short conclusion, which says that the details of these calculations, together with full exposition of our techniques, will be given in a forthcoming article. Furthermore, we hope to obtain a simple analytic form for the answer, making our result not only an experimentalist, but also a theorist's delight. Not clear what they meant. When you look at this, how you, what do you, yeah.
Just out of curiosity, how many people check this calculation?
I'm not sure, probably, well, not in the end, what I say on the next slide, probably nobody at that time, because they used supercomputers to do these calculations back in 1984. So I don't think they were reproduced. So maybe this calculation was never reproduced. But the result which was reproduced was the formula they found in the following year, which is one-line formula for these whole 14 pages of algebra. So there was an extraordinary simplification. And of course, by now we understand why the result is so simple. Yeah, so from today's point of view, it's not mysterious, but back then it was extremely mysterious. How is it possible that such a complicated calculation, when each term is quite complicated, has such huge cancellations, and you get a one-line formula? And now in the subsequent years, people try to explain it, use it, kind of get some wisdom, and develop new methods which would exploit this simplification. Actually, despite the simplification, the simplicity of that result was understood in subsequent years. This is a kind of a special process. They use some special helicities and so on.
So
But
this is already sample.
no, this is one special helicity, one special. So if you do arbitrary helicity, then it's slightly more complicated by today's, but we can write in from today's point of view on 2 lines. Yeah, but this is one special helicity. It's kind of the first non-zero helicity. It's called maximally helicity violating amplitudes. The full understanding of why is it simple was actually only in 2008 because of finding some hidden symmetry in 3-level amplitudes of gluons, which then extends to loops in certain theory, not in QCD. I will talk about that a little bit later. Yeah, but so there is a symmetry argument for why is it so simple, but nobody knew about that back then. Okay, so let me now talk a little broadly about the amplitudes and where we start, where do we go. So this kind of raised the question in the following years and in early 1990s of can we actually find a new definition of the amplitude? Can we approach the problem in a different way? So we definitely have the standard approach, the perturbative QFT and the methods of Feynman diagrams, which works extremely well. At weak coupling gives us a prescription for any quantum field theory, which makes sense in this context. But there are these simplifications that we cannot see. Now, there was also an old method, which predates QCD, which was used back then for pion scattering. And that was trying to fully fix the amplitude using some physical principles. This is called analysis S matrix program. This wasn't successful back then because kind of the problem was too hard. Yeah, taking the pion scattering massive amplitudes and trying to fix them non-perturbatively, not even in perturbation theory, is just two difficult problems. And today we also have no idea how we would even approach it at the moment. So the modern methods, which kind of came after this Park-Taylor and other subsequent calculations, was kind of use some of the spirit of this, thinking about the amplitude as a unique object fixed by certain properties, but at the same time work in the perturbation theory and use Feynman diagrams when needed to kind of check consistency of our results. But the idea of amplitude being a unique object fixed by physical principles has been a kind of extremely useful paradigm and the playground for further progress. So let me say just a little bit what do I mean by amplitude as a function. So for me, it's a rational function of kinematics. This is what the amplitude is at 3 level. At loop level, we start with the rational function of external kinematics, momenta, and also loop momenta in these loop diagrams, and we have to integrate over them. Now, once we integrate over them, we get the actual amplitude we are interested in, but this is a very complicated objects in general. The space of functions which appear after integration, we don't know. Yeah, we have, there are results at 1 loop and 2 loop. We have pretty good understanding of the function space at 1 loop completely, at 2 loop partially. But beyond that, these are some polylogarithms, generalized polylogarithms, elliptic functions. We don't generally know. However, the structure of these rational functions encode a lot of properties of these functions post-integration. So this is one of the main tools that people used in recent years. People who are interested in doing these integrals is study the structure of the integrands and try to see what inherits the answer after integration. So I will mostly talk about these rational functions. At some point, I will also say a few words about that, but most of my focus will be on these rational functions. But the experience is that once you understand them extremely well and write them in a very suitable form, it makes this next step easier. Actually, today's most of the work on these loop amplitudes is not doing explicit integrals, but solving some differential equations. You just derive some differential equations for these objects and then you solve it, and it originates from the differential equation for the integrand. Yeah. This is not universal method. You have to find the equation, and a priori there is no way how to find it. You just have to try. But this is how people who are doing integrals, what do they mostly do? Yeah.
Uses, is there a small parameters that tells you that differential equation is justified?
Yes, yes, and there are different ones. So some people do differential equations which use in in dimensional regularization, the parameter epsilon. Sometimes it's kinematics, that you kind of take a derivative with respect to external momenta or some cross ratios that you can make from the external momenta. So it can be different things. Yeah, there is no kind of universal rule. There is no universal rule how to find the differential equation for a given diagram. So it's kind of a creative work, yeah, at the moment. Yeah. Okay, but the nice thing about these differential equations is that they play extremely well with these special functions which appear. Yeah, because they satisfy differential equations, so you kind of try to find that differential equations. Yeah, it's a lot of art. Yeah, yes. Yeah. No, that's an extremely good point. So the most useful differential equations are one which reduce the L+1 to L. Yeah, so you basically hit the function at L+1 and you get a source term on the other side, which is L. So these are the most useful equation, especially if you want to do some sort of resummation, then the same type of equations can work for that. Yeah, excellent. Yeah, it's an excellent point.
Should such relations exist in general, or is that going to be special case?
You have to find them. Yeah, they don't exist. Yeah, unless you have like some, of course, you can have differential equations which are related to some symmetry properties of the amplitude, conformal symmetry or things like that. But these are typically not, they are not very strong. Yeah, so these don't even give you, yeah. So the examples of equations which we have, which kind of go from one loop to the other loop, these are differential equations in kinematics. Yeah, so it's something like that. If you hit logarithm with a derivative, you get a rational function. So in this sense, you kind of jump between the loop orders. Yeah, so, okay, perfect. All right, so just to kind of repeat the point that I already said, so what we strive for is some notion of uniqueness, that this object is unique and constructible from certain constraints. So we would like to find the constraints which specify, we will mostly work with these tree-level amplitudes here, but in principle also these loop integrands, which uniquely specifies the amplitude. And once we have these conditions, we would like to invert the process and reconstruct it from these conditions. Yeah, and this is kind of a technical thing, but what seems to be true, that once you find enough constraints which tell you this object or this object is a unique answer to that question, you can always invert it and calculate it from that. Yeah, and we will see this will be the idea of recursion relations, and all these methods are always based on that. But let me just tell you what these constraints are, at least in the context of these tree-level amplitudes, things which don't have any internal loop. And these are just rational functions, just from the get-go. And two principles that we have is locality. And in the context of scattering amplitudes, it means that if things interact in space-time, they interact at one point. And because the amplitudes are written in momentum space, this translates to having a special form of propagators in our amplitude. So these are rational functions. There is some numerator factor. There are denominators. And the denominator are products of things which are sums of momenta squared. And this is manifest in Feynman diagrams because the Feynman propagators exactly have this form. And so this is a general feature for any amplitude. And the second property is unitarity in this perturbative context. So SS dagger is one, but we are doing it just in perturbation theory. And for tree-level amplitudes, this boils down to a statement that if we calculate the residue on this pole, if we go close to this pole kinematically, the amplitude factorizes into two subamplitudes. And here, all these external lines are on shell. We are talking about physical particles. P squared is equal to m squared. If we talk about massless particles, which we mostly will, P squared equals 0. And we get a factorization into two subamplitudes. And this is also manifest in Feynman diagram approach, because you can always look at one of these lines in Feynman diagrams. You can set it on shell. You can say that this is a physical particle, and you kind of build two of your subamplitudes on both sides, on the left and right. So these two basic properties of amplitudes are manifest in Feynman diagrams. What is not manifest in Feynman diagrams, and that's what causes a lot of problems, is the gauge invariance. Yes, please.
The question of previous slide.
Yes.
Is this square dependence, quadratic dependence on P properties of small momenta or a generic property?
This is generic here. Yeah. So this is so sorry, I write P square, but this is for massless particles. If we had massive, we get P square minus M square. Yeah.
But it's no higher powers of P.
No. If there were no higher powers, we would work in some non-local quantum field theory, which we can in principle, but we work in local quantum field theories when we have canonical kinetic term. Yeah. But there is an interesting point when the propagator is different, but then we are a little bit outside of what we do. We can go in that direction, yeah, but we don't here. Yeah. Okay, great. So, okay. So if the amplitude is fully specified by these conditions, so we have some rational function, it has a bunch of poles, we say exactly what these poles are, and we say what this function should do on these poles, then if there is a unique answer to that question, then we can kind of invert the process, as I said, and we can use something called recursion relations. This is some on the mathematical level, this is using Cauchy's formula and reconstructing the function from its poles. This is just a technical implementation. But the physics idea is that we take all the lower point amplitude. So if we know the amplitude up to n-1, we can recurse this information and calculate endpoint. There is nothing new in endpoint which is not in n-1 and -2 up to the fundamental amplitude. Okay, which means that you can basically recurse everything from the basic building block, which in most of the theories we are interested in are 3 particle amplitudes, but it can be also 4 particle amplitudes in certain cases. Yeah. And this is so this is called BCFW recursion relation. This is the original version, and then there were many other versions afterwards. And this is just the comparison in case of gluon amplitudes at 3 level. This is the number of Feynman diagrams. This is what I quoted before, but then it of course grows with more and more external x. And the number of recursions, number of terms in these recursions is very small compared to it. So this is a very efficient way how to calculate 3-level amplitudes. Now, just to kind of emphasize the connection to the Feynman diagrams, you can say that I said that I reconstructed the function from the poles. But if I look at Feynman diagrams for gluons for 2-to-2 scattering, the 4 particle amplitude, I will have a Feynman diagram which does not have any pole. It's a contact term. So you can say, how can I reconstruct this term? This doesn't have any pole. Well, the problem with Feynman diagrams for particles with spin is that they are not gauge invariant by themselves. So you are not really describing the correct number of degrees of freedom. So the gauge dependence of this diagram is linked to the gauge dependence of all other diagrams, and only the whole sum is gauge invariant. So despite this thing doesn't have any pole, it's already prescribed what it should be once you include the terms with the poles. Okay. So in other words, the Young-Mills amplitude, the gluon scattering, is reconstructible from its poles. Despite in the Feynman diagram approach, you naively have contact terms which don't have any poles.
So
yeah.
Kind of theory, like a theory that I use to find a fourth term or something, that I could draw all the same diagrams.
Yes.
That are not like by gauge invariance.
Right.
So in that theory, I can't get the 4-point.
Yeah, you cannot. You have to kind of supplement the information about the 4-point. Yeah.
Is there a way for me to look at a theory and know whether or not it's
so, well, it's actually, there is nothing much mysterious about it. It's just you have to count what is the number of independent coupling constants in the Lagrangian, and as many amplitudes you have to supplement. In Young-Mills amplitude, there is only 1 coupling constant, so you only have to supplement the most elementary. If you have a theory with 2 coupling constants, you have to give me 2 kind of seeds, and that I can recurse it. Yeah, from that. Yeah, I cannot rederive your independent thing. Yeah, you have to give it to me in some form. But you can ask further, and this is what I wanted to say here. So this is the first slide with here, the magnifying glass. So you can ask, what happens? Can I do something with the amplitudes which are not fixed by factorizations? As you asked, they have more coupling constants. But what about they have infinite number of coupling constants, which would be kind of they exist. I can take some general effective field theory with many coupling constants, and I can try to calculate amplitudes then. And then in principle, if you go to endpoint, they are just not reconstructible because there is always a contact term at any number of points I cannot calculate. And this is true. So these theories are not reconstructible. However, I can ask, is there any special theory in this class of these general effective field theories which have special amplitude, which is reconstructible? So this is kind of going backwards. Normally, we would already start with some theory and calculate amplitudes. Now I'm asking, in the space of amplitudes, is there any special point where the amplitude is reconstructible, which would correspond to some special Lagrangian, probably with some special symmetry in it? Yeah. And so I can play this game and I get interesting things. So I can start with Lagrangian for scalars, which has two derivatives, and I write infinite power of terms. I can calculate amplitudes here. They depend on momenta and also on these free coupling constants, which are unfixed. And now I need to impose some additional condition, because just writing the Lagrangian already guarantees that my amplitude is local and unitary. That's no longer a condition. Once you have Lagrangian, then it's local and unitary. Well, as long as your Lagrangian is local. And now I impose additional condition. And the additional condition can be, for example, and that's extremely useful one, is vanishing in certain kinematical limits. So in particular, if I send a momentum to 0, I declare that the amplitude should vanish. And as it turns out, if I do it in this case, if I just consider single scalar, I get 0 because this is a reparametrization of free field theory. All the amplitudes are 0. But if I allow to have multiple scalars, I get non-zero amplitudes, and all these coefficients get fixed by imposing this condition in terms of the leading interaction terms. And what I get is SU and nonlinear sigma modal amplitudes.
It's a three-level statement.
Three-level statement, yeah. So this is a three-level statement only. Now, of course, this Lagrangian has a shift symmetry. This was the reason why there was a soft limit in the first place, but I kind of reverted the things. I imposed soft limits, and I got the result, which is known since Adler from 1969. But I rederive the thing from the amplitudes point of view. Now, I'm rederiving the stuff which is known, but this is a general framework in which you can search in the space of amplitudes, looking for special theories. And yeah, in a given theory, there must be a symmetry, which is responsible for these special kinematical properties. But this gives me a tool, because searching in a space of things with special symmetries might be hard or not super well-defined, not super well-defined method, but searching in a space of amplitudes with some properties is very well-defined for the tree level here. So we are only looking at tree-level amplitudes. So the way how to generalize this approach is in multiple directions. I just give two examples. I can just add more derivatives, yeah, and just say that my terms have more than two derivatives. Yeah, for example, this is one of the possible series. So I have a derivatively coupled scalar. And then I impose, again, some behavior in the soft limit. In this case, some stronger vanishing when p goes to 0. And it uniquely fixes all coefficients. And I get something called dBi action, which is interesting from various point of view. It shows up in the low energy limit of the string theory, for example. I can also prescribe that the soft theorem, the right-hand side, is non-zero. So it doesn't vanish, but it goes to some prescribed function, yeah, that I know, for example, n-1 point amplitude. And then as a solution to this kinematical problem, I get also some interesting nonlinear sigma models with various properties. Now, the same ideas have been also applied to some non-relativistic systems, not just talking about relativistic quantum field theories. Again, the idea is that I start with Lagrangian, I calculate the amplitude, and then I impose some conditions, and I try to fix the parameters to find something special. So, so this is definitely one direction of research. People also try to add masses and other things, and just to see, can you see it as can you rederive the Lagrangians and the field theory, the field theories from the properties of the amplitudes, rather than the other way around, start with the from the theory and calculate the amplitude. Now, going now back to this idea of recursion relations, it's interesting because just constructing things at a higher point from lower point is such an elementary idea that it could just, one can just think that it was invented very early on. Maybe for gluon amplitudes after the QCD was formulated in 1973. But actually, it took until 2005. So it took basically 30 years to people to realize that you can use this recursive method. And the reason for that is that if you do this recursion, you have to start at the smallest point amplitude. And it turns out that in Yang-Mills theory, in gravity, in many theories, is the 3-point amplitude. And if you talk about 3-point amplitude for massless particles, these are 0 in the real world. So how to make sense of these recursions if your seed is 0? Yeah, so that was the bottleneck until Witten in 2003 wrote a paper when he basically just said, okay, these 3-point amplitudes are 0 for real kinematics, but they are non-zero for complex momenta. Well, they are not realized in nature, but I still calculate them because they are useful. And that basically kind of opened the new window. And 2 years later, with Brito Cacciazzo and Feng, constructed these recursion relations. So I will now talk about these 3-point amplitudes because I think this is a nice kind of elementary thing. Yeah, they are very special and they kind of underlie a lot of the later progress in various parts of this amplitudes field. So the simplest amplitudes are 3-point. As I said, they don't exist in the real world. We don't have a decay of massless particle to other massless particles. The reason for that is just kinematical. So if I have 3 massless particles which are on shell, so P1 square, P2 square, and P3 square are all 0, and I satisfy momentum conservation, so P1 plus P2 plus P3 is 0, just the solution to these constraints, it's extremely constraining, is that all kinematical invariants are 0. Yeah, because P1 square is P2 plus P3 square from this equation. The squares are 0, so also all the dot products are 0. So naively, there are no kinematical invariants the result can depend on. Yeah. The only exception to that is actually phi cube amplitude, which is 1. Yeah, so the scalar amplitude when the amplitude actually is 1. But from the kinematical point of view, there is no kinematics it can depend on. However, in 4 dimensions, something special happens. And we find 2 discrete complex solutions to that. So just to say here, there are no kinematical invariants. Of course, this has a solution when all 3 momenta are parallel. Yeah, so all 3 momenta being collinear is a solution, but there is no amplitude you can write for such a thing, yeah, because there are no kinematical invariants. This is too degenerate configuration. But if you consider complex momenta, not just real, you can actually find a solution. And this is best seen in so-called spinor helicity variables. So let me just quickly go over it, but you can skip it. It's just kind of technicality how to do it. In 4 dimensions, you have your momentum has components P0, P1, P2, and P3, and you can instead of writing in a vector 4 component, you can also write it in 2x2 matrix like this. And the condition that the particle is on shell and massless is that the determinant of this matrix is 0. Determinant is P squared. And because the determinant of a 2x2 matrix is 0, you can write it as a product of 2 vectors. And we call, because it's only rank 1, this matrix. And we call these vectors lambda and lambda tilde. And this will be our kinematic. So for each momentum, we have lambda and lambda tilde, 2 component vectors. And then the scalar product P1 dot P2 actually factorizes into 2 terms. One is a contraction of 2 spinors of one kind for particles 1 and 2, and the other one is a contraction of the spinors of the other kind. So in order to send P1 dot P2 to 0, you only need to send one of these brackets to 0. So there is some special factorization of kinematics in 4 dimensions, which allow you to send this to 0 and not basically sending all of them collinear at the same time. In D dimensions, you have no other choice. Yeah. And in these variables, they are useful for many reasons. The Lorentz transformations are particularly nice. So little group transformation, which is something which changes the momentum. Sorry, that's the transformation which keeps the little group transformation, leaves the momentum invariant. That is just a simple rescaling of these lambda and lambda tilde spinners. So anyway, so there is a lot of nice for massless particles are very conveniently written in terms of these variables. And then the two solutions are that all the lambda spinners are proportional. So all the brackets of this kind are 0. All the lambdas are proportional. All the brackets of this kind are 0. So this is just kinematics. There are two solutions for 3-point kinematics. And now if you have massless particles in 4D, they are described by two helicity states, plus and minus s. It's massless, so you don't have all these states in the middle as for massive particles. And now you can just write down the free particle amplitudes for any spin, or for any helicity. There is no restriction. You can choose helicity -2 and +3 and -4. There is no restriction. Nothing restricts you to go to higher spin massless particles. We know that these things don't exist in nature. We will see it just in a moment why they don't exist. But at the level of free particle amplitudes, they all exist. And if we write them, I just remind you that this corresponds to complex momenta. So if you kind of go back to momenta, these momenta are complex, because the real momenta restrict you, all the momenta being collinear, and there are no amplitudes. So this is a little bit academical kind of discussion of 3-point amplitudes for complex momenta for any spins. But the point is that these things will then feed into higher point amplitudes, and they will put significant constraints how they look like. Okay, so let me look at gluon amplitudes because they are interesting for our discussion. If you look at spin 1, you have two helicities, plus and minus. So you can consider different combinations, 3 minuses, 2 minuses, and plus, minus and 2 pluses, and 3 pluses. And based on these little group transformations, you can just write out the formulas. 2 of the cases corresponds to these kinematical solutions when all these brackets of one kind are 0, so they only depend on this type of brackets, and the other 2 solutions corresponds to the other kinematical solution when this was 0, and therefore we get only these brackets here. Now, once we specify the helicities, the amplitudes are unique. You solve 3 equations for 3 unknowns, and you just directly write down the formula. So the kinematical part is unique. Of course, you can multiply by some coupling constant, and the coupling constant gets renormalized and so on, but the kinematical part is unique. The only thing you can change is some number in front of that. Now, and we don't have to say here in which theory we are working, because for this amplitude, there is only this expression, nothing else. You cannot say, well, I work in some other theory and I have other expressions. No, there is only one expression, which also means that you can see from the structure of these brackets, these are only generated in F³ theories, and these 2 are only generated in F². Yeah. So if you look at this helicity in Young-Mills, it's 0, because it's only generated by the F³ term. Okay. All right. So in Young-Mills theory, only these 2 helicity configurations are allowed. All right. Yes.
Young-Mills or Maxwell, whatever.
Yeah.
Effective field theory, aren't there?
No, I just mean that you have only F². You have non-abelian gauge theory with F² Lagrange. If you add F³, you can edit. You can edit, and then you generate these 2.
As an effective field theory,
you will have all of them. Yeah, as an effective field theory, you will have all of them. And yeah, you definitely have them. You have also F⁴ and so on. They don't contribute to 3-point, but they will add something new at 4-point and so on. Yeah, I'm just saying that if you say we are working in strict Young-Mills theory, you will not have these 2 helicity configurations. You will only have these 2.
But can you see from this construction that the F³ will come with extra powers of some cutoff or something?
It will have for kind of kinematics. Yeah, so it has higher derivatives. Yeah. So kind of the number of these brackets count number of derivatives, basically. Yeah. So it's kind of 3 derivatives. Yeah. It's more derivatives. Okay, good. So this is just a short summary that these 3-point amplitudes are very special, fixed for any spin. They exist, best written in terms of these spinor helicity variables when it's obvious, or what are the kinematical solutions and how to build them. Now, so But now, in order to go to higher points, I want to calculate a higher point amplitude. And now the big condition on the higher point amplitude is that, for example, at 4 points on the pole, it must factorize into the two products of 3 points. That's what we said was this basic property of locality and unitarity. And this puts extremely strong condition of what 3-point amplitudes I can possibly have, because my 4-point amplitude must factorize to them. And if I am careful, if I impose all these conditions from factorizations, I actually find that all these higher spin stuff is forbidden now. Everything which is spin bigger than 2 is not allowed. You don't find any 4-point amplitude which factorizes into 3 points. The spin 2 must be graviton, just a single particle, which couples equally to other fields. Spin 3½ is only consistent in the SUSY multiplet with gravitons. And then spin 1 must be Young-Mills in the leading derivative coupling, or it can be F³ if you go to higher derivatives. And spin 0 and 1½ are less constrained. So bigger the spin is, more constraining are these factorizations, and spin bigger than 2 is actually completely forbidden. And yeah, this type of ideas about imposing factorizations and also then at loops, some cuts of the loops has been used with constraining the SMEFT operators and doing other things. Once you turn on masses, things become less constrained, because then even the 3-point amplitudes are not unique. And you get constraints, but it's not as rigid as the masses. The masses are really rigid. Of course, for massive states, we have higher spin. Yeah, we have atoms and like bigger objects, and black holes. People also do these calculations, so they do exist. Yeah, so but you still have this condition of factorization even on massive balls. It gives you conditions. It's just not that constraining. Okay, so now let me kind of switch the gear to something I have been working on. So this general idea of fixing the amplitude from constraints is kind of very broad, and people do it for different reasons depending on their particular problems. So there are many different methods that people use. It's kind of just like overall overreaching idea. I put constraints, I get the results from it. Yeah? But my own work on amplitudes was not only that, but has been mostly centered about a new idea. That amplitudes can be taught as mathematical objects, in particular, some differential forms on geometric spaces. As that's surprising and alien as it sounds, it has a very logical origin, which I try to explain now. And the ingredients here are 2 ingredients. The one is combinatorics, and the other one is geometry. So the combinatorical part tells us that we need to get a very good control on all the singularities of the amplitude. Poles, factorizations, anything when the amplitude blows up, basically, or all different limits. And this information can be reduced to some simple combinatorics. I will show the examples for that. These combinatorial structures then label boundaries of the geometry. So I take this and now I put it into a different place. And now they will label some boundaries of the geometry. And this geometry will be built from kinematics, from momenta of my scattering process. And the amplitude then can be reproduced as a volume, differential form, or something else that we don't know for more general theories on that geometry. So this is the basic strategy. And the type of geometry which appears here was described by mathematicians only recently, only a few years ago. And they gave it name positive geometry. And it's actually very simple. It's not even that fancy as the geometry which appears in string amplitudes, Calabi-Yau, and higher genus things, and so on. It's very simple geometry. You just start with some polynomial inequalities. Like this one, you have some linear and quadratic or some higher inequalities in some parameters. These parameters will label kinematics for us, but in mathematics, these are just some parameters. And you look at the interior, and that's your geometry. It's the space which is cut out by these inequalities. For us, these boundaries will correspond to singularities of the amplitude, the poles when the amplitude blows up. And then for this geometry, you can define a canonical differential form which blows up on the boundaries. So whenever you approach a boundary x is 0, it gives you dx over x. It blows up. and the remainder thing is the differential form on the lower dimensional boundary. So this is all, this is a full definition of what this geometry is. The simplest example is just a line segment. This is a positive geometry, and this is just saying that x is between x1 and x2. And the differential form looks like this. It blows up on boundaries. It blows up when x is x1 or x is x2. And that's our quasi-amplitude in this case. Yeah, this is actually a simplest amplitude, which I will present just in a second. Even this simple example already means something physically. Now, the two prime examples that we have is gluon scattering in some special supersymmetric theory, this one, and a scalar scattering in phi cube theory. Here, it's an all-loop order statement, tree-level, and loop integrands. Here, this is a tree-level statement, despite there is now generalizations to loops, but involves more things, which I will not discuss here. We have more examples of partial constructions. When this thing is not going that far, for example, it's only combinatorics, it's not yet the geometry, or we don't have the volume form or things like that. Yeah. So here the thing is that we don't have a general recipe how to find the geometry for a given theory. It's like one by one, you just have to find it. Yeah, you have to study the amplitudes and try to see if you can find the geometry for that.
In these
Yeah.
geometries, like, is there any physical meaning to the sign, like greater than or less than?
No, well, no. It's the geometry has a sign, but you mean flipping the sign? It's being like outside the geometry rather than inside. So, okay, the sign, the meaning is that you would like to be inside.
Yeah, but like, it'll give me the same amplitude if I put some of these.
Not necessarily. So, for example, if you take this boundary and flip it outside, you get this region, not this region. So the sign is important. Yeah.
Well, wouldn't it give me like the same omega? Like the...
No, it wouldn't. The inequalities will be different. One of them is flipped. So the form is different for that. Yeah. The inequalities are different. Yeah. So you would describe this region, not this region, if you flip, for example, this sign of this inequality. We can discuss it later. Yeah, I can show you some examples. Okay, so let me just say that it's important that these are colored amplitudes. For some practical reasons, we need amplitudes which are ordered. Yeah, so if you think it's some large and limit of the theory. Yeah, let me just say that the colorless theories are not understood in this context. We don't have the right variables to define the geometry. Okay, so this is kind of a timeline of how the progress went in the last 15 years. We have now different examples of these geometries. Only very recently, the mathematicians were able to prove the conjecture we made 11 years ago. So now the conjecture that this reproduces the amplitude is actually proven at tree level at the moment, yeah, despite the conjecture is at all loops. Okay, so let me give a quick kind of sketch of what this geometry is for this phi cube theory. So in the simplest case of phi cube theory, the 4-point amplitude is a sum of two Feynman diagrams, which is given this formula. And the geometry, the labeling of the boundaries is following. Each boundary corresponds to one of the channels, the S channel and T channel. And the bulk kind of corresponds to a contact, yeah, or no channel at all. So there is an S pole here and P pole here. This is in analogy to what I said before with the line segment positive geometry. Now, if you go to higher point, this was actually studied by mathematicians. So all the cubic graphs, which are the Feynman diagrams of the phi cube amplitude, have been understood combinatorically as labeling edges and vertices and faces of a polytope called associahedron or Stashev polytope. This is a polytope of dimensionality n -3. So if you go to higher point, it grows. So this is for 4-point, this is for 5-point, this is for 6-point, and so on. Let me just show how it works for the polygon at 5-point. Each vertex is one of the diagrams of this kind. If you, so there are 5 ordered Feynman diagrams. If you go to two neighbors, they share one of the propagators, and the other one is, if it is collapsed, it gives you a contact term. So the edge corresponds to this diagram. And then you can fill it for all others. So this gives you a combinatorial prescription. Each diagram actually corresponds to a singularity. This diagram corresponds to a singularity when these two kinematical invariants are 0. And that works also for higher points. Now, the question is how to reproduce the amplitude. This was just combinatorics, this first part. For that, you have to find the good variables. And even in this 4-point case, we have one-dimensional geometry, but we have two variables S and T. So we have to find a line in the S and T space which would correspond to that geometry. And it's one line like that. So in general, we have too many kinematical variables and only n-3 dimensional space. So let me skip this. This is the explicit construction of these new variables. This was found in 2017 by ABHY, and they find the right variables in which you can construct this geometry. And once you have the geometry, you can reproduce the amplitude using some simple canonical form, the one that I defined in this context of positive geometry. And the way how to calculate the amplitude is to triangulate the geometry. Because if I give you this pentagon for 5 points, you don't know which differential form you write. But once you triangulate it in terms of triangles, each triangle has a simple differential form that you can immediately write. And then you just sum over them. And different triangulations gives you different expansions for the same function. Okay, so now in just a few minutes about the amplituhedron. So this works in this planar n equals 4 super Yang-Mills theory. This is a very special theory with many connections. For us, it's a toy model for QCD. Of course, it misses some important properties of the QCD, but captures some other ones. So this is a UV finite theory, has no confinement, and has convergent perturbative series. So these are definitely the properties that we don't have in QCD. From the other point of view, three-level amplitudes are the same for gluons in QCD and in this theory. And the loop amplitudes are simpler. For example, they are not UV divergent. But the leading part, in some sense of the special functions, is very similar and in some cases the same. So it's our toy model for QCD, doesn't capture everything, captures some of it. But this is where we can construct this construction. So it has these three parts: combinatorics, geometry, and obtaining the amplitude from the differential form. The combinatorics will be related to permutations. The geometry, there are some new variables we have to define, and we need to rebuild this geometry from the kinematical space. And the canonical form will be actually the same that I showed before in the associahedron. This thing about the permutations, so let me just do the combinatorical part. It's kind of interesting because it's a new way how to think about permutations. If I want to represent the permutations graphically, like 1 goes to 5, 2 goes to 3, 3 goes to 2, and so on, I would draw a diagram like that. I can think about this diagram as a scattering in 1+1 dimension, when here is the time and here is the space, where the interactions are 4-point interactions. I can think about it like that. But the question is, and there are some moves that don't change the permutation. So if I take this line, 2 goes to 2, and I move it across this point, it is the same permutation. This is called the Young-Baxter move. But the question is, can I do permutations using only 3-point vertices, not 4-point? And so if I have a 3-point vertex and I start from 1, I have to decide, do I go left or right? And so that means that I have two different elementary operations, going left or right. So I have two different white and blue vertex. One when you turn left and one when you turn right when you hit the vertex. And if you build the diagrams from these two types of vertices, these are called Pleby graphs, studied quite recently by mathematicians around 2005 on kind of the mathematical, normally it might take 100 years or a very long time to do these things, but they were accidentally studied very recently. And you can, any permutation you can associate with such a graph. And there are also some identity moves on these graphs which don't change the permutation. And for us, these graphs have a role in physics because they exactly give us all the singularities of these gluon amplitudes. They tell us where are the factorizations. They tell us about the loop level singularities. So this is exactly our combinatorial way how to say where the amplitudes blows up. What are the singularities? So if you want to reconstruct the amplitude using these recursion relations, which you can, you only have to specify a small number of permutations, which gives you all the invariant information about the amplitude. Okay, so this is an extremely compressed way how to specify what the amplitude is. Because permutations are enough to label all the building blocks that are needed. Okay, and then building the geometry, there is some construction. It's not difficult, it fits on one slide. But in the end, the geometry is labeled by 3 parameters, n, k, and l, which in physics means number of particles, number of loops, and some helicity number, which tells us which particles are positive and which particles are negative helicity. Let me give you an example. So in the simplest examples, these geometries are polytopes. More complicated, they are not, so I cannot draw them. So this is just the example when I can draw it. So this is some particular gluon amplitude. And it's given by this polyhedron that you see. And I can cut it into tetrahedra. I have natural triangulation in terms of 4 pieces. And I have also Feynman diagram triangulation, which gives us 34,000 pieces to cut this thing into 34,000 pieces. Of course, the Feynman diagram triangulation is also special. It does some important things, but it cuts it into many pieces. I can find some special gauge choice, do some smart things, and only cut it into 9. So I can kind of find 9 Feynman diagrams using a very, very special gauge, which is exactly designed for these helicities. And only 9 out of these 34,000 diagrams survive. So Feynman diagrams are also interesting triangulation, but it depends on this gauge choice. You have to fix it very well. So this allows us to access some all-loop order data in this theory. So the problem is set up in a way that I can say what is the all-loop order amplitude as an answer to certain question. So the geometry in the end gives us these inequalities, which I said before. So these 2 lines are inequalities for some parameters of the loop momenta, which is translated in this kinematical space. If you solve these inequalities, you will write what is the amplitude at arbitrary number of loops. These inequalities are very hard to solve, despite they are very easy to state. Yeah. Here, the labels, you are basically taking all possible labels. Each of them runs from 1 to L. This is a set of L² quadratic inequalities in 4 L parameters. So mathematicians don't know how to solve them. But I can formulate the problem as a simple set of inequalities. If some genius comes and solve it, we would solve all loop amplitudes in this problem. We have some newer work which does some special triangulation and only takes kind of the throws out the complicated pieces and only keeps the simple pieces, and we can do the all loop order resummation of that. So let me skip that, but we are getting some kind of interesting comparison to the exact results which are known from integrability. Not quite matching the full result because we are doing approximation, but definitely better than anything you can do with Feynman diagrams. The only thing that you can resum at the level of Feynman diagrams is to resum ladder diagrams, and they give you some exponential suppression, which at strong coupling, is exponentially suppressed. So we have only these specific examples. So the main goal for future is to find some general dictionary, how to go from a theory to a geometry. We don't know that. We don't know how to do that. We don't know how to build a geometry for a theory that you give me. We know how to do it for Lagrangians and Feynman diagrams, but this is exactly what we are missing for geometries. We can just do it one by one. Study the amplitudes, change variables, find the combinatorical structure, find the geometry, calculate the volume. But how to add massive, how to add interactions, we don't know in this picture. So that's the biggest challenge for the next decade, probably. The special place is the special place are graviton amplitudes, which let me skip that. Let me just say that they have very unexpected kinematical properties, despite there is no a priori physical reason why they should be nice. Yeah, the gravity is not renormalizable theories. Why, if you look at graviton 3-level amplitudes, there should be anything nice. But for some reason, there is something nice, which suggests maybe for some geometry, but we don't know. Yeah, but this is something I'm actively looking at. So let me end with an outlook. So the amplitude fields in general is a very wide field. People are doing different things, doing many complicated collider physics calculations, application to gravitational waves. It's the most recent one. My work mostly fall in the exploring of the new theoretical methods, which kind of connects to the other dots, but it's not directly related to the applications, but it might have some potential maybe. Now, this interaction between physics and math, this is something relatively recent. There have been very crucial interactions. We ran into the same object roughly 15 years ago, both physicists and mathematicians, physicists on the side of amplitudes. And then we define new objects, including this amplituhedron, and the newest is the surface hedron defined by Nima. And they still don't fully understand, the mathematicians, what these objects are, but they are very, very new, and their existence is very surprising to them. And they are interested in studying it. But for me personally, what is kind of the most appealing here is that we are finding surprising new things in the standard physics. So these gluon scattering and all these things is just a standard physics. There is nothing speculative. These things have been around for 50 years. And the fact that there is something new in them is surprising. And it took roughly last 10 years to get to the point that we can be at least partially confident this is not a curiosity. And hopefully the reformulation of the standard physics might lead in future to solve some more major important puzzles in the particle physics. The general way of thinking in this field might be potentially applicable to other problems. Studying functions, generate theoretical data, calculating the objects even beyond just amplitude, study singularities, limits, hidden properties. Can you fix the things from these properties? Can you recurse them? Yeah, all these tools I think might be more generally applicable than just for amplitudes. And just onward looking, we don't know where this will go. Yeah, so we don't know with which other areas of mathematics or physics this program will eventually interact. Thank you very much.
We have very limited time for questions, maybe one question. Yeah, no, it's okay, but we have to leave in 1 minute.
Question.
Yeah.
Maybe a little bit just condensed method driven. You showed us wonderful way how to essentially some higher order Feynman diagrams.
Yeah, okay.
But what about radius of convergence general of perturbation theory? Are you certain that the finite radius of convergence is not zero?
No, it is zero. It's definitely zero. For our theory, for this very special planar n=4, it is finite. Yeah, because there are no non-perturbative effects. It's very special combination of being UV finite, not having any renormalons, and being large n limit, having no instantons. But in a general theory like UCD, there are definitely non-perturbative corrections, and it's something beyond. So that's even the farther step. First, understand perturbation theory, and then there will be something missing, and that would kind of allude to non-perturbative effects.
Right. The perturbation theory itself, about the combinatoric factor at each order will grow n factorial. Then you will get zero radius of convergence, just conventional expansion.
In the conventional one. Yeah. And we will not change that. Yeah. So in the general theory, it's definitely zero radius of convergence, and you have to calculate these non-perturbative effects. Yeah.
Some special.
Yeah, for some special theories, when you have these extra structures, then it is finite radius, but that's not a generic feature. It's not a generic feature.
All right. So let's thank Yara again, and
Thank you.
I think that's it. And we'll take